So we've got our two vectors here. So the direction angles, there's nothing fancy here. You just have to know that each of the direction cosines is given by whatever component in that axis direction is. So in this case here, if I'm looking for the angle to the x-axis, it's just the x component over the magnitude of the vector, and so on and so forth. The y component over the magnitude of the vector, and then the z component over the magnitude of the vector. Okay? And we shouldn't be surprised here that we are seeing an obtuse angle here and two acute angles. So we expect that when the vector's on the other side of the axis, or the positive part of the axis, that the angle to it will be greater than 90 degrees. Okay? So any issues with this one here? So we're not going to do, you're going to actually see we're going to do very little with these direction cosines. In fact, I can only think of one time when they're ever going to come back, and it's more as an example than anything else, because as we're starting to see, we don't really work with direction explicitly when we're doing our operations. Okay, so I'll assume I can move on, otherwise please stop me. So here in particular, I'm looking for the magnitude of this vector. So the first thing I do is I calculate the vector. So just take my time, try not to make any silly mistakes. And then once I have a final vector, I just use my magnitude formula to calculate the magnitude. All right. So these would be, your typical, one-off knowledge and understanding questions. Okay. Here, now, one of the things that, in fact, is going to it comes in handy, we're going to see in a few occasions, is this idea of coming up with a unit vector. But notice here, though, I'm looking for a unit vector in the opposite direction to v. So I'm not, should the one be negative? Oops, which one are we talking about? Here? Two, 5, negative 1. Oh, yeah, very good. Thank you very much. So that should be, I'm going to go fix that. This should be, because I'm multiplying by this here. If we go back, we see that it's negative 2, 5, 1. So when I multiply by the negative, it should be 2, negative 5, negative 1. Okay, so there we go. Get a little smaller. Probably didn't need to do that. All right, thanks, Kieran, for noticing that. Okay, so again, this is something that you definitely need to know how to do, is to take a vector, and to create a unit vector, you just have to divide by its magnitude. The only extra little hitch in this question was I was looking for something opposite to v, which is why I needed this negative 1. All right. Here, using the standard basis vector. So notice here I use the symbols instead of writing this as negative 3 times 1, 0, 0, 4 times 0, 1, 0. I might as well use these symbols. So y, I, j, and k are the official symbols for our three standard basis vectors. All right. So essentially, it's just the x component times I, the y component times j, and the z component times k. All right. Any questions on number 1?
Sorry, Tony.
Yep.
For question C, I think it was the unit vector. We just have to divide by the magnitude, right?
Exactly.
Okay.
Okay. But since I needed the direction opposite to v, instead of working with a v, I worked with negative v. Okay. Of course, minus my little mistake there. Okay. Anything else for question 1? All right. So let's go to question 2. And this one here we'll talk about. It says determine the values of P and Q if, well, what should step 1 be of this question? So who can tell me what I should be doing first? What would I like to see on both sides of this equation? Yeah, so eventually, how do I get to that? What's the first thing I should be doing? There you go, is I should be trying to write the left-hand side as a single vector. So I've got two vectors that are equal to each other, and then I know the x components are going to be the same, and the y components are going to be the same. Okay, so here that's what I do. I distribute, You know, notice here, I try to make an effort, you know, even if you're adept at these things, this is where you make sign errors, is if you try to go from here directly to there. It's not that bad an investment to actually write out this step, okay? And then lo and behold, what do we have is we have an expression in P and Q, which has to be equal to 13, and then another expression in P and Q, which has to be equal to -9. And so this is where we've got our system of equations. So I'll just show the rest of the solutions here. So this is my equation that equates the x components, and this is the equation that equates the two y components. And then from there, I just solve it as a straightforward system of equations. Okay? So here, this is just, you know, an exercise in doing vector algebra, in this case here, distribution, addition, and then equating two vectors. But of course, I'm going to take this a little further and ask you a question. What's special about vectors -2, 3, and 3, -1? What might they act as if I'm able to write any other vector as a combination of these two vectors? What do we call such vectors? Okay, let me see some of these are basis vectors. So remember that we have our standard basis vectors, you know, I and j, or in 3D, I, j, and k, but in fact, there's lots of vectors that can act as basis vectors, okay? So I could find P and Q such that this combination could give me any vector in 2D. And who's going to remind us what the conditions are on these vectors? So let's get some other people to remind us, what are the two conditions we have to have on those vectors so they can act as basis vectors? Okay, so you can't have one of the vectors be the zero vector, and you can't have those two vectors to be parallel to each other. Clearly, these are not scalar multiples of each other, so they're good as basis vectors. Okay, any questions on this, or move on?
Yeah.
Yeah.
Just a question to get, if I were to get full marks on this, would it be enough to, what I did, I kind of just skipped the first two lines where you have the two like coordinate points. I just skipped directly to the part where you have the therefore symbol.
Yeah,
Would
and you know what? I'd probably give you full marks for that, but if you made a mistake, it would be more than just a half-mark mistake than if you made the mistake in doing this here. Because if you somehow get to something that's incorrect, I then have to ask myself, what kind of error was that really? So it's the usual thing. Skipping algebra is perfectly fine, you know, as long as you don't go from here to there, you know. In fact, a question like this would often have the caveat you can't just guess and check, okay? But yeah, that's not a problem. Just, you know, don't make a mistake. Otherwise, it would be actually quite a big deduction, okay?
All right. Okay, cool.
Okay,
Thank you.
great. So let's go to 3 here. So again, what did you have to notice in this question that made it solvable? Otherwise, it's not particularly solvable. What was, okay, there you go. We saw that it's U hat and V hat, which tell you that these are unit vectors, okay? So essentially, this is a lot like, you know, the problems we solved, maybe, you know, slightly more complicated than the one we solved in the official quiz. So essentially, I've got my two vectors that placed tail to tail make an angle of 110 degrees. But the idea here is if I multiply one of the vectors by 3, it's keeping the same direction. So it's not changing the angle between the two vectors. The angle between u and v is the same as the angle between u and 3v. Okay? Now, had this been u minus 3v, well, then you would have had to arrange your diagram to take that into account. Okay, so here it's the usual thing. I take this vector, I move it over, and I solve my, my problem here. Okay, and here, what do they want? They want give the direction relative to vector u. I probably started drawing this diagram before I really looked back. Personally, I guess I should have put the u in the horizontal position. That would have been the better thing to do. But in the end, hopefully I didn't make a mistake. So here, use cosine law to find the magnitude, okay? Then I found this vector here, and it turned out to be 19.47, okay? But because I didn't think ahead, I realized, oh, wait a minute, they want the angle from vector u. So I had to calculate this angle phi, which would just be, well, 110 minus my 19.47, okay? And there you go. So there's my answer, 2.82, 90.53 degrees from u towards v, okay? Would have saved myself that step if I had thought ahead and put vector u here so that the angle I found would have automatically been from the vector I wanted. Okay. So main thing here, when you see a hat, remember it means magnitude 1. And, the thing that you had to sort of come across was that just because I multiplied vector v by 3, it didn't change the angle between the two vectors. All right. Any questions on this one here? Nope. All right. So let us move to number 4. What do we have here? Piece of art suspended 2 nails, centimeters apart, using these 2 strings. And they tell us the tension in one of the strings. So it's a little bit different from some of the questions we've seen. Okay. And they want us to determine the tension in the other string and the mass of the object. Okay. So again, if you chose to solve this using components, perfectly reasonable. Okay, so I started off with my usual situational diagram. So what's going on? I've got my 3 strings, and similar probably to one of the homework questions, but different from the one we solved in class, was the fact that I didn't quite give you any direct direction information. But the idea here is that, and maybe let's draw, see if I can manage to do it this time. If I draw this horizontal line here, which is parallel to the ceiling, what I'd really like to find, what I'm looking for, is the angle from the horizontal to that vector. And the same thing on this side, the angle from the horizontal to that vector. But because these are parallel lines, these 2 angles are the same. So I use the fact that I know the shape of the triangle via the side lengths to help me find these 2 angles. Okay? And again, you notice that first one I have to use cosine law, and the second one I choose to use cosine law because I just don't want to be involving myself in any issues with the sine law. All right? So any questions on how I set up the situational diagram?
Yeah, I have a question.
Yeah.
Could you solve this using like similar triangles?
You mean in terms of the
Because you're given like a ratio like 50 and then 110.
yeah, okay. And
then
that's
you have-
yeah, I'm just trying to think if there's any reason why that wouldn't work. I don't think you can assume that the amount of force in the string is necessarily proportional to the length of the string. Okay. I would imagine that that's not correct, but interesting to see what you get as an answer. But something tells me, like, if I'm not, you're just kind of, for me to go right off the top of my head, I'm not 100% sure that it's proportional. It could be, again, like that's what happens when you don't take physics for, wow, almost 30 years. You forget some of these things. All right. So let's take a look at my force diagram. So now that I have these 2 angles, I'm able to draw my force diagram and come up with a bunch of angles inside. Okay, so I'm going to guess the first thing I do is find the tension in the string L1. And again, why am I not worrying about the sine law here? Why is that of no concern to me in this particular scenario? I'm always talking about worrying about sine law. Why don't I worry about it in this scenario? There you go. Is you're working with two angles and one side length. And of course, once you know two angles, you actually know all three of them. Okay, so the shape of the triangle is set already. Okay, so here's my tension in string 1. Okay, and of course, I'm going to find the force due to gravity, but that's not actually what I'm looking for. So there's my force due to gravity. Okay, again, using the sine law, but I'm looking for the mass. And let's see if we can show that here. I don't know if you can see that. It's right at the bottom. Is I use my F equals ma. I know that the force is the mass times acceleration, so I just solve for the mass. All right. So again, a slightly different take on a couple of the ones we've seen before. You could probably come up with, the same, so you come up with what 4 or 5 possible questions that one could be asked from this type of question. Okay, any other things we want to ask here?
How did you find the internal angles in like the force diagram?
Okay, so here what I said is well, hey, look at this force here. It's in the direction of the string. So if I can find the direction of the string, I'll know the direction of the force. So you see where my cursor is? That's the angle that I'm trying to look for. That's this 44.4. But because this horizontal line that I've drawn is parallel to the ceiling, which I've assumed is horizontal, this angle that the force makes to the horizontal is equal to the angle phi that I've drawn there because it's parallel lines, okay? So from there, this angle phi is inside the triangle made by the strings in the ceiling. So I use the fact that I knew the side lengths of the strings and the distance on the ceiling. I know the side lengths of this triangle. That allowed me to find phi, and then phi is the same angle as this here. So that's where the 44.4 becomes the angle that L1 makes with the horizontal. Okay? And then a very similar argument for this angle that L2 makes with the horizontal is equal to that angle there. So this 34 you see appears right here. Okay, does that make sense?
Yes, thank you.
Okay, anything else before we move on this one? Nope. Okay, so let's take a look at number 5. So it says find all vectors parallel to the vector -2, 5 that have a magnitude of 10. And there's a couple of ways. You'll see that I'm going to show a couple of scenarios for solving this. So first of all, how many vectors do I actually expect to find? If you think intuitively. Yeah, because you sort of think that whatever this vector is, okay, say this is the vector, and obviously it's not the vector -2, 5, but I don't care. I'm just using the diagram as a guide. Well, I have to figure that in this direction, there's only one vector in the same direction that has magnitude 10. But of course, parallel doesn't necessarily mean in the same direction, could also be in the opposite direction. So it makes sense that there's only 2 vectors that would be answers to this question. So does somebody want to tell me how they solved it? And maybe somebody came up with a third way. I've got a couple of scenarios here. Anybody want to say what they did in general to solve this problem?
So for me, I imagined it like kind of like a circle.
Okay, yeah.
So, and because from the question, the x component is 2 times less than the y component, I did like a circle function. It's like x squared plus half x squared is equal to 100.
Interesting. Okay, I'll be interested to see that. Now I noticed you said half. Like this is not quite half though. Were you using
Right,
the ratio
2.5.
between? Okay,
mean,
so use 2.5. Okay, interesting. Actually, I wouldn't mind seeing that solution. That's an interesting take on that. I don't know that I've seen that before. So if you can send me that in an email, I'd be interested to take a look at it. It's great. Anybody else have something different that they want to share?
I just said that a vector parallel to -2, 5 would be some constant k times that, and then you distribute it, and then you can just plug that into the magnitude formula.
Okay, there you go. And that's going to be my second option. Okay, that's going to be the second option that I show. And in some ways, that's maybe the most direct way of doing it. Okay, I'm going to show you something that's a little different. Okay, except it's going to look like a lot of work just because I really showed all the work very, very carefully here. But what I did is I said, let me find the unit vector in the direction of u, which is just this vector here. I just took -2,5 divided by its magnitude. So again, I probably normally would not show all this work. I'm just trying to be very explicit. But now what I have is I have this unit vector, say that's magnitude 1. So if I want the vector in that direction that has magnitude 10, I just multiply the vector by 10. And if I want it in the opposite direction, I just multiply by -10. Okay? So it's kind of like a little indirect way of getting to the answer, is you take the vector you're interested in, create the unit vector, and then multiply that by 10. Okay? So it's a nice, quick, easy way. There's not really any solving involved. But I would say the more direct way, and I don't think I did all the steps here, but the more direct way somewhere here is going to be is to say, well, if it's parallel to -2,5, then it means that it's going to be of the form some constant k times u. And you need this vector to have magnitude of 10. So, like, I don't know who said that. Was that Anna? It sounded like Anna, maybe? Or
Yeah.
So, okay. She took the k, she multiplied, so that's -2k and 5k. She put it into the magnitude formula, made it equal to 10, and then solved for k. And lo and behold, look what we get for our k values, positive or -10 over √29. Multiplied by the vector gives you the exact same answers. Okay? So a more direct approach. What's this? You can also use primary trigonometric ratios. Yeah, probably. Okay. Yeah, I'd like to see that one. I'm not going to do it here there because it might take too long, but send that one to me. I wouldn't mind seeing it. It's always nice to see different. Yeah, that looks like it would work. Okay, except make it, I guess, take that unit circle and make it magnitude, make it radius of 10 or something like that. Okay. So anything else we want to ask about this here? So again, this is kind of like your old 2-mark thinking question, which it's not that it's that difficult, but you kind of have to see either, some approach to it. Any other questions we want to ask about number 5? Your question. Oh, sorry. Wait a minute. Shouldn't the question say collinear instead of parallel? Parallel and collinear essentially mean the same thing. They're equivalent terms. Okay. I think in the notes I use the word parallel, but collinear, parallel mean exactly the same thing. Okay. I should actually add that in the notes. That, like I said, I define that as being parallel. Collinear is the same thing. All right. Is that good, Gleb? Okay. Okay, thanks for bringing that up, because I think the book probably uses the word collinear sometimes, means the same thing as parallel. Okay, let's take a look at the last one here. Oops, I was supposed to hide this, but I guess I forgot. I guess if I, pretend you didn't see that here, and, so I'm looking for vectors whose direction angles are all equal. In other words, alpha has to equal beta, has to equal gamma. Sorry, exact answers for which question are you talking about, Kieran? Last one? Well, actually, the one we just did. Yeah, the one we just did. Ideally, yeah, if it's not an application question, although because we're dealing with, especially if there's no angles involved, you probably should give me exact answers unless there's some kind of application. Okay. So here I need alpha equal to beta equal to gamma, but if those 3 are the same, I'm claiming that these 3 have to be the same. Okay, makes sense. Okay, cos alpha will also have to be equal to cos beta, also have to be equal to cos gamma, okay? But then if these are the same, I can start equating what they're equal to. So x over magnitude of u has to be equal to y over magnitude of u, or x over magnitude of u has to be equal to z over magnitude of u. I guess I should have, by the way, one little thing I don't like about my solution here is I should have defined that u was some vector x, y, z. Okay, a little lazy of me there. Okay, but then because I can just multiply both sides by magnitude of u, I get that x has to be equal to y, and x also has to be equal to z. So what does that tell me about y and z? If they're both equal to x, they're equal to each other. So in other words, the condition that you need is that all three components have to be the same. Okay, and I don't think that should be too surprising. You know, think about it in 2D. If you're looking at the angles between, you know, the line and the x-axis and the line and the y-axis has to be the same. It's going to be right down the middle. It'll be the line y equals x. So not surprisingly that in 3D this should be the case. So in other words, what do all your vectors look like? Any vector of the form I called it AAA would satisfy these conditions. Okay.